Okay folks, this is going to be the Fuzzing Part 2 video for FSU. This is just a quick 45-minute, 1-hour presentation. We are not going over Part 1. If you're interested in looking at Part 1, you can go to csg.utdallas.edu. This site is no longer correct. Make a note of that. And you can check out Part 1 there if you're interested. Part 1 simply goes over more theoretical aspects of fuzzing, what types of values you want to use, how you might enumerate an application to find its inputs. It's more theoretical. This is a purely hands-on section, Part 2. It's literally how to program a fuzzer in Python. It is just programming the entire way. So if you want a little more background, you can check out the first presentation. So the outline, we're going to cover some debugging libraries for Windows. This is going to be PyDBG and WinAppDebug. We'll go over some examples in both of them and how to create the programs. We'll go over the pros and cons between the two, and then we'll talk about some designs for your fuzzer, what goals you want to have, and I'll talk a little bit about the one I had at the time that I created this presentation. So let's talk about debugging libraries. PyDBG is the first one we're going to talk about, and this is the one that I'm most familiar with. This is a... I hate that stupid thing. Okay, this is a pure Python 132 debugging interface, quote unquote. And this is part of the PyMay reversing engineering framework. That is a fantastic framework by Pedram Amini. You should be following him on Twitter, and he's a badass, and there are other really cool tools in the PyMay framework. Including PyDBG. So what exactly can you do with PyDBG? Well, like your normal debugger, you can launch or attach to a process, you can set your breakpoint, step into and over stuff, you can read the contents of memory or your registers, and give you access to the process environment block, disassemble things. All these normal things you could do with a debugger, except it's scriptable, and you can do it within Python and automate everything. So it's very, very handy. And another neat feature is that since it's Python and you can use IDA you can use PyDBG within IDA. So that's pretty cool. So, and again, you know, how is it different than just regular Ollie or Immunity or something like that? It's scriptable. So you could automate things like unpacking malware. Maybe you want to get some general statistics, or you want to profile a certain process. You can definitely do that with this. If you want to do fuzzing like we're going to be doing, then you can catch signals that are interesting to you. You can actually do in-memory fuzzing with snapshots. Pretty cool stuff. You can take a snapshot of a process and fuzz it, revert it, all in memory. And let me close that event. So, okay, let's just dive into the examples. So, right off the bat, Python is really simple. You can import the PyDBG library, and in 3 lines of code you can create a PyDBG object. You can call the load function, which is going to load up whatever executable it is you're interested in debugging, and then run it. So pretty painless, nothing going on here, and this would just launch your application. In this case, your notepad would pop up and your notepad would be running. So we need to get a little more in-depth than that, and one thing that PyDBG is really good at is callbacks. So we can just run the application by loading it and running it like the code shows here, but we want to catch interesting signals. If we're going to be fuzzing an application, yes, we're going to run it, but we also want to make it crash, and we want to be able to catch when that happens. So we can catch signals using callbacks in PyDBG. So in this case, we're going to use the set callback function on our debug object, and we're going to pass it the access violation signal. And when this happens, we want to call our callback function handleAV. So now there's nothing fancy going on in handleAV. We're just going to print access violation, but now we at least have the ability to catch signals of interest and have a callback function that's associated with it. So, and that's a good point, a little note down here. On Windows, an access violation is when a process tries to access just invalid memory. I think we go into detail on that later. And so this is an example, it's a screenshot of that happening. So in this case, there's just a program being run. It's iCrashAlot.exe. I think it was just like a 5-line C program that tries to dereference an invalid value, which triggers an access violation, and it's caught here by PyDebug, and the handler is called. So now, why exactly do we care about access violations, and what's the whole invalid memory thing? So this is memory that is not mapped within the process, or it could be memory that has incorrect permissions if you're trying to execute non-executable memory or read non-readable memory. This will also trigger an access violation. So when we're fuzzing, we're commonly trying to influence pointers or values, or you're messing with boundaries, and you cause things to walk off the edges of memory segments. So an access violation is usually a good indication that you had some critical influence in the application, and now it's trying to access what possibly was valid memory, but you've had some influence over it in some way, so it's invalid memory. So this is a really good signal to catch, especially when you're fuzzing. Another one that it notes here is illegal instruction. So this usually means that you started executing in executable memory, so that was fine, but maybe you were off by a couple bytes, so you started executing in the middle of an instruction or in just a data section that's executable, and it's not a valid instruction. So you've had some influence over the instruction pointer in some way. So illegal instruction and access violation are two good signals to catch. So we're going to go into a little bit larger of an example here. And this one we're going to launch the application, or you could attach to it, whatever. We're going to set our callback handlers, and we're going to run the application. Now that's the same so far, but this time we want to collect as much information as possible about the crash. So when we look at it later, we can see, is this an interesting crash? Is this one we want to try to replicate? Is this one that could be exploitable possibly? So PyMe comes with a great utility, crashbinning.py. And this, if you just pass it your debug object, automatically returns a lot of great information. So here's the crashbinning.record crash, and all you do is you pass it your PyDebug object. You can pause this and look at it if you want to see the definition, but we'll go over some examples in a second. So in this case, we have the exact same code as previously. We create our PyDebug object, we set a callback function on the access violation signal, we load iCrashAlot, and we run it. The difference is in our handle AV function. So instead of just printing access violation and then returning, in this case we're going to use the crash binning. We're going to call utils.crashbinning.crashbinning, pass it our debug object, and in this case we're going to go ahead and print the crash synopsis that the crash binning utils gives us. So you may want to save this to a file or something, but we're just going to print it right now. And this is what it looks like. So here we run our Python PyDebug 3, which is going to run iCrashAlot, and right away it comes about, this is the output you get. It says, iCrashAlot on the instruction move into EAX, the dereference value of EX caused an access violation when attempting to read from deadbeef. So we can see you get the register dump right here, and it's helpful enough that it'll actually try to dereference a value for you. So 0 is non-dereferenceable, or it's not pointing to valid memory, so it just says NA. But a couple of these values, they could be pointers, so it goes ahead and tries to dereference them for you. Now, most of these don't seem to be useful, but you can actually see it. ESP+4 is a pointer to iCrashAlot.exe on the heap. So that's interesting right there. The other thing you get is the disassembly around where the crash happened. So we know from the top up here that move EAX into the dereference value of EAX was the faulting instruction. So, and that's this line right here. So it gives you a little bit of disassembly before and after the instruction. And you can see here that I think I just tried to dereference dead beef in the source code because it just moves dead beef into EAX and then tries to dereference it. So that's just triggering the access violation. You also get your a backtrace of your stack and your structured exception handler. So with these 16 lines of code, I mean, you load an application, you run it, you set a callback, and you get fantastic debugging output on the crash. So this little crash binning utils is extremely helpful and saves you from having to try to iterate over all these things and do it yourself. So yeah, that's the basic PyDebug intro. Now you can import your multiprocessing, you can spin up a bunch of processes, and you can start fuzzing and mutating some files. The next thing we're going to talk about is WinApp debug. So WinApp debug is sort of the new kid on the block, and if you were going to do just Windows debugging, I would use WinApp debug instead of PyDebug. It uses C types to wrap some Win32 APIs, and it's intended for QA and fuzzing and stuff like that. So again, why not just stick with PyDebug? Well, at least a little while ago, PyDebug had become a little bit more OSS focused, at least on the newer stuff. I love PyDebug and it rocks, but it's getting a little bit old and outdated, and you might have to write a couple wrappers around it, depending on what you're trying to do. There's some pretty good tutorials for setting it up, it's not too bad. But WinApp debug, if you're going to do Windows only, it's probably the way to go from now on. So the WinApp debug site actually has some fantastic examples on instrumentation, debugging, and other miscellaneous stuff. So we're just going to go over one briefly, but check out their site for some great information. So that's a good note. We're going to compare our last PyDebug example to accomplish that exact same goal in WinApp debug. So we were at 16 lines, this is at 24, however I've also got 4, 5, 6 comments in here. So code length wise, it's pretty much the exact same, but let's pick it apart a little bit. So we're going to import WinApp debug, excuse me. And similarly, we just create an object down here, we say load this application, and loop instead of run. So sort of similar. Now the difference is in the callback. You create a callback handler class that inherits the event handler. And now whatever signals you're interested in catching, you create a little function for them. So in this case, access violation is one we're interested in, illegal instruction is one we're interested in, and all I've set it to do right here is just call my own custom handle signal. And in here you could, print your data or whatever it is that you're interested in doing. So very similar, except you create a little class that inherits event handler, and then it's going to automatically call access violation on an access violation signal or illegal instruction on an illegal instruction signal. So pretty similar, and not too much of a difference. So here's the one large example that we'll step through for WinApp debug, and I think this was directly from their site. So this is hooking the WSPrintf function, and in order to do that, we first catch the load DLL signal, and then we resolve if it's user 32 or not, or we check if it's user 32 or not. If so, we resolve the WSPrintf, we hook it, and then at runtime we're going to print the arguments. So the first thing we have, just like in our previous example, we have our event handler class that inherits an event handler. Now, instead of defining access violation or illegal instruction, in this case we're just catching the load DLL signal. Now, at runtime when that's hit, we can check, does the module that's being loaded match user32.dll? And if so, let's resolve where the WSPrintf W function is within it. So this is going to return the address within the module user32 where this function is at. So we literally have the address of it now in memory. And now we're going to hook it. So there's this neat little hook function, which basically just sets a breakpoint for you and an associated callback with it. So now at runtime, we've figured out where WSPrintf is, and it's hooked. So at runtime, whenever that address gets called, our callback function is going to be triggered. And within here, we grab the format string off of the stack, and we want to count the number of arguments, and we're doing this by counting the number of % signs in there for format specifiers. Then for each one of those, we want to read that many D words off the stack. So read stack Q words or D words, depending on 32 or 64. And then print them to the screen. So this is relatively short to catch a module being loaded, resolve a function, set a callback, then set up and then have the code for the callback that at runtime, figures out how many arguments are passed and read that many D words or quad words. So WinAppDebug is pretty powerful. You could do it similarly in PyDebug, but WinAppDebug is probably going to get you a little better bang for your buck, considering it's much more supported and updated. So this is cool. At runtime, you would be seeing every time this function got called, you'd be seeing what was being printed to the string. So that's a pretty neat little example. Now, there are some other really fantastic ones. They have watching variables and buffers and some other really cool examples. So check out their site if you're interested in WinAppDebug. It's a really good site with several very useful examples. So now we're going to talk about some fuzzer design. So you've seen how with a relatively little amount of code you can get a process up and attached to, set your callbacks, and then run it. But there are some other pieces to the puzzle when creating your fuzzer that you want to take into consideration. Good fuzzer design is very important. So like any other piece of software, there are a couple overarching goals that you want to keep in mind. You want to be modular. So in our example here, we're going to separate out sort of our generator, our executor, and our monitor. You want reusability. Speed, obviously. If we're fuzzing, we probably want to get hundreds of thousands or millions of iterations of something. So speed is definitely something you want to keep in mind. Now that probably means you want it to be multiprocessing or maybe even distributed, rather than just a single process mutating a single piece of data and feeding it to an application. And you also don't want any false negatives. You certainly don't want to miss what could be an awesome crash. That sucks. So a little bit about modularity. What are the general tasks? We have to sort of outline them that need to happen during fuzzing. So here are a couple of them, and one of them is you need to generate your mutated data. This could be generative, so you could literally generate something, or you could just mutate known data. You'll have to launch the target application. You'll have to send it the data in some way, and you'll have to monitor the application for the signals that you want to catch, the access violation, the illegal instruction, etc. And you probably want to log the results. I'm sure you can think of a couple more as well. But these are our general tasks that any fuzzer sort of has to do. So you sort of have this little cyclical pattern here where you mutate data, launch the application, monitor the application, and log results. And so this cycle is something that you just sort of want to follow when you're fuzzing. Now, in the example we're going to be going through here, we have these sort of set up into 3 different pieces: the mutator, the executor, and then the actual fuzzer itself, .py. So, and again, part 1 of the presentation, if you look it up, it discusses possible values you may want to try. So just shoving random data into a file, for example, isn't going to yield you the best results. Or think of integers, for example. If you have a field, a field is going to contain a length value or is an integer, maybe you don't want to do random, maybe you want to do like 0, -1, maxint over 2, +1, and -1, so on and so forth. And those values are discussed in part 1. So the mutator here, in this example, simply yields a new file name back every time. So for every offset in the file, and then for every value in your mutation values, it's going to write out a new file with the bytes in that location mutated with whatever values you specify here, create the file, and return you back the name. So maybe you don't want to create a new file every time, or maybe you do. This is just one option for a mutator. And here's the executor. So it looks long, but it's only 50 lines, so it's not too bad. At the time of writing this was my actual executor. It is no longer the case. At a high level, what's going on is it continually checks an incoming queue for new jobs to execute. When one is available, it executes it, and depending on the output, it will catch any crashing output and then send the results back to through another queue back up to the parent, basically. So initially, when init is called, we just set up our values that we were passed, including the timeout, a pointer, or our in queue, our out queue, and then we enter the loop. So when we're in this enter loop function, this follows sort of the poison pill technique, where it just continually tries to read from the queue. And if the object that it was passed was a string that happened to equal a stop, that's our poison pill, and we'll break out and end. Otherwise, it continually just tries to read from the queue or sleep, read from the queue or sleep, until finally it receives an object. Now, once it gets the object, it executes it, which calls our execute function. And this should look pretty familiar now. We just set up our PyDebug object. In this case, we were just setting two callbacks, one on the access violation signal, and one on this user callback debug event. So I believe the next slide talks about it, but this is called every iteration within PyDebug. So every like between every single instruction that's executed, this is called. And the access violation we set to the callback function to be handle AV, and this user callback function, this user callback signal, excuse me, we'll call the timeout callback function. And what the timeout function callback does is just check to see if a certain amount of time has elapsed within that process. So maybe the process hangs, or maybe something happens. We don't want to run it more than 10 seconds or 5 seconds or 2 minutes, whatever your timeout, whatever you choose that to be. This just makes sure that the time that process has been alive doesn't go beyond the timeout time. And so it just terminates the process. In handle AV again, this should look familiar, where it just calls the crash bending utils, gets the debug output, and then we set these variables in our object that can later be retrieved. So, and this just sort of mentions that again, handle AV we've seen before, and the timeout is just a custom callback function. Every iteration of the main debugging loop, that's a nicer way to say it, it gets called. And this was sort of my workaround to create a timeout. At the time I didn't see another way to do it, at least not a native API way to support it. So this was just the workaround for creating a timeout. Now this is the actual fuzzer itself. And I think this is the last big block of code we'll stare at, so bear with. But when the fuzzer is initially created, there's an incoming queue and an outcoming queue created, and then we have a list of processes that are initialized to 0 initially. We open our log file, and then the start function is called. So the start function creates our consumers, or the basically the executor function that we just saw. So let's say you want to run this with 5 processes. Well, then this would iterate 5 times and then create a new process each time using the multiprocessing library. So it creates a new process. Target equals executor. So when you create a new process with the multiprocessing library, target is the name of the argument that contains the function that the new process is going to start executing at. So when this new process starts up, it's going to start executing the executor function, which was this function right here, executor, that we just discussed. So this is going to create, however many of these you specified, and they are each going to enter their loop and start listening to the queue. So we're going to create our monitoring thread, which is going to pull the output back from processes that have been executed, and then create our mutator, which is going to mutate the data. Then it literally just, in this case, it mutates, I think in this case we just iterate over the file and we get a new mutation of the file until we've completely gone through every byte or every D word or quad word in the file, whichever this is set to, I don't recall. And so for every one of those mutations, we add them to the queue. This is the queue.put, and it puts a little dictionary in there saying this is your new file name, this is, you know, the offset, this is the value that's been mutated, and it just sits in the loop and continually does this. So you can feel free to grab my Fuzzer on GitHub. That is the collection of all these things. It has all three pieces put together. It is a work in progress, and and this is no longer true. It does follow a consumer producer model. It is no longer a multiprocessing. That's not true, but it is multiprocessing, but it's now distributed. So while this was the architecture in the presentation we just had, there's a fuzzer with a mutator that continually loops in here, getting new iterations or new mutations, and it puts the new data for the consumers in the queue, and then these consumers continually pull the queue, execute the data, or execute whatever they're told to execute rather, and they place the results in an outgoing queue that the monitor reads back. That is what was just shown in the previous slides. In the current iteration that's up there, it's distributed, so it uses, I forget the library now, but it uses a networking library so that you can distribute this across multiple computers or locally if you want, and you can spread the load out a little bit. Yeah, so like we discussed, for each file in the mutator, we're going to create a new mutated file, we add this job to the queue, the executor is going to execute it, monitor the job, and then place the results in the outgoing queue. And so yes, there is actually an incoming and an outgoing queue, but I didn't want to change the graphic. So how could we improve this fuzzer? How could we get better odds, or how could we get more useful information out of the fuzzer? There's a couple things. One of them that would be really neat to add would be code coverage, and this is sort of keeping track of where your execution flow is within the program. So if you're commonly taking one path within the program every single time and then it's bailing out there, well, maybe we want to figure out how to take a different branch somewhere within the program to avoid whatever this pitfall is that we keep on falling into. And now PyDBG and WinAppDebug both support process stalking, which does the program flow monitoring at the basic block level. So it's pretty cool, and it definitely is something that could be done. It says make this a cluster instead of a consumer producer, and that's sort of what the new version up on GitHub is currently. It's distributed and communicates over the network, still following the incoming and outgoing queue, but it's distributed. And you could also add support for specific file formats and fields instead of the way it is currently. Or you could just use Peach for specific file formats, that is. So another question is, where exactly can you get your sample files? Obviously Google comes to mind, and there is a file type filter you can place, file type : and then whatever file type you're interested in. So file type : zip will give you a list of zip files. Be careful with Google. If you don't have the Google API key, then they will eventually limit and or block you. So be careful with that and don't get your university blocked. These sites have examples as well. Be careful. I'm sure there is tons and tons of malware on there, so just be wary as you peruse those sites. And some further resources. Grey Hat Python is a fantastic book, and there is a section on PyDBG in there as well as some other things. And then if you want more of a book dedicated solely to fuzzing, Fuzzing Brute Force Vulnerability Discovery, this was a fantastic book. Very, very useful. I highly recommend it if you want to get more into fuzzing. If you've done a lot of fuzzing before, there may not be much value in it, but if you're new to it, this is a great book to get started with. And that's it, folks. I appreciate the time.